Lesson on week 5, and I'm Subham.
Good evening, sir.
Good evening. And
evening,
this session
sir.
is solve with us assignment, solve with us session on week 5. So it is like I have some slide. In that I have some question for you. We will discuss those, and maybe that questions belong to activity or maybe practice or similar to somewhat graded maybe also. And this session is like not only as a solve with us, you can ask your doubt. Like we will do the same thing. Same thing means two things, like make as ad open also, and solve with us also, solve with instructor. Like you can ask your doubt, and in that in between we will discuss whatever I have prepared those question. I will discuss those also, and like your conceptual or
Sir,
activity practice related in.
Sir, when can I ask my doubts?
Yeah, so please raise your hand first. Because in starting so many.
okay, sir. Hand is already raised.
Yeah, so one by one, please raise your hand so that.
Sir, I have problem in this topic, isomorphisms.
Sir, and I was not able to get a linear transformation.
Yes,
Okay.
sir. Yes, sir. These are the problematic topics. I am stuck since yesterday in this topic.
Sir, don't we have open session for this week?
Yeah, actually there's this session is it's like solve with us, and when is your this week 5 graded over?
So Friday, this Friday, 10th of June.
Yeah.
So there will be a session then for week 5, because of the quiz there was no session. Now today is one session, and next session will be on 7 to 9 probably.
So 9th session, it's for week 6 open session.
For week 6,
Yes, sir.
as usual time will be, but there is one more session on 9. I think
You can schedule tomorrow because we
Yes, sir. Yes, sir. Let it be tomorrow at the same time.
Like if you can teach the whole week again, like Subhajit sir did in the last week 4, sir.
yeah. So next
Sir,
session
or
will take Subhajit will take.
Yes, so
Or-
is best.
sir, you may extend the deadline by 1 or 2 days, if
No,
possible.
whatever the deadline is, that is the operational kind of like.
Okay, sir. No problem. Then can you arrange one session tomorrow?
Yeah, one session will be sure, I think, on the 9th. That's why I'm saying, and maybe timing they will you will inform soon. What is the timing and what is the exact date? Probably it will be on 9 for week 5, and the usual time will be Friday and Saturday. The next Friday and Saturday will be for week 6, like that.
Sir, I am seeing in my calendar, open session is for week 6 from 6 to 8 p.m. So
Okay.
can we arrange one session from 8 to 10, but they would be back to back? Would it be possible?
No, as usual, sessions will be continue. There is one extra session for week 5 is on 9. That's all. There is no rearrangement or there is nothing.
Sir, are you discussing the concepts of week 5 today also?
Yeah. It will be like probably it is like a open session. Your doubts will be. Then I have some question in the. If you will get time, then we will discuss those also. Like that.
Actually, is it possible like how Subhajit used to do same way?
So it will be like because of there is only 2 sessions. Yeah, I will try to be like that, but let's see. Yeah, I will try to be. It may be like that. Let's see. Okay,
Hello,
so,
sir.
yeah.
Sir, all the topics in maths 2 are related to vector space, or is there any new topic? Actually, out of curiosity, I just asked the question.
Hello, sir. Hello.
Just one minute.
Hello.
Yeah, just 1 minute.
Okay.
Yeah, okay, you may continue now. So what
Yes,
is
sir.
that?
Sir, for the vector based, suggest some books, sir.
Yeah, there is one book already mentioned in the portal. You can
No,
see
sir,
that.
no, sir. There is no book for the vector space.
No, there is. Uh,
Yesterday mentioned one book which
no, there is
actually depends on
one
data.
book.
There is
Sir,
nothing.
sir, I want to ask one thing, that in week 6 there is a kernel or something, kernel size image. So it is related to, I read that it is related to the neural network something, batch normalization and all the things. So it is related to that or it is different?
It is related to.
Neural network, that kernel size, filter size in the deep learning.
Oh, no. So it is a normal thing. Like, what is the kernel? What is linear transformation? Then what is the related to the kernel null space of matrix, like that?
Okay.
There is yeah, you will see that. Yeah, because of that,
Huh.
see, you will see the application of these things in the deep learning.
Yeah.
So that's why it is here. This concept, basic concept, your approach, mathematical approach. You will see the application in the next courses.
Okay. And so one more thing, that week 3 and week 4 lecture, actually I am able to watch. Lecture means the live sessions.
Okay.
And from Saran sir video, actually I'm not getting 100%.
Okay.
Yes, sir.
So,
Yes,
sir,
sir.
so sir, it is.
I'm not getting, sir, isomorphism and this linear dependence.
And so week
I'm
3
stuck.
and yes, sir. So without week 3 and week 4, the coming weeks are not.
Yeah, it will be difficult because all things are based on vector space.
Yeah. So, sir, the Subhajit sir's and yours video for week 3 and 4 sufficient, or I need to refer some books or some other open source lecture?
It's depend on if you watch. Then Subhajit is taught very well. If you see that, it will be, I think, enough, and along with the video lecture. First, watch the video lecture, get some idea, then watch the session. Then it will be more clear to you.
Okay. No, sir, I watched the Saran sir videos, but yeah, I'm unable to get all the things. But yeah, I watched the first session of week 3 for the axioms and all the things. So
Rohit,
yeah,
watch the live sessions. You can view the recordings on YouTube.
Yeah, I know.
It would clarify much of your doubts.
So yeah, first thing, please, please make like raise your hand one by one. Yeah. So Naveen is want to ask about what is the isomorphism. Is that?
Yes, sir. Yes,
yeah.
Sir.
So see, if you know the linear transformation, let me tell you what is the linear transformation.
Yes, sir.
So linear transformation is nothing but a mapping. Mapping means a function. Linear transformation are function, like you have seen function fx is equal to something like x square. This is a function from R to R. Okay, this is a real line. So see, this is a function. So linear transformation is also a function. Like the differences is it will be on the vector space. Suppose, let's say, let me write that this is a function from V to W. I am thinking V as a vector space, and W is also as a vector space. So if there is a function with such relation, there is a function from vector space to vector space with which having a properties like this. If let's say this is an element, or if you are saying this is a vector space, so this is a vector, this is another vector, so it will behave like this. If these two property hold for this function, then we will say this is a linear transformation. That's all. There is there is no difference in the function and linear transformation. Linear transformation is nothing but a specific function. Specific means having these two properties. That's all.
Okay, sir. Sir, we can think of it as a function like V is the domain and W is the codomain.
Codomain, yeah. V is actually here. See, this is a function, so V as a domain and W as a codomain. Yeah, domains and codomains are vector spaces.
Yes, sir, that I got.
Yeah.
Sir, what my problem is in this lecture, sir. The examples which Sarang sir discussed in the video lecture. I got, sir, he has discussed example 2 seen earlier is not on isomorphism, the non-examples.
Hmm.
The first one I get it, sir.
Hmm.
He has also discussed the fifth example, R from R3. Like the domain is a real line,
Okay.
and R3 is three-dimensional space. So,
Okay.
sir, can you explain this example? I have made my
I will.
reasoning.
I will. Yeah. I will. Yeah. So what is the like
Easier-
R is
Yeah.
as a domain? So means saying to be R is a vector space from. So think R as a vector space over R, and R3 is saying to be that this is a vector space over R3. Means, sir, have whatever have taken like those are the vector spaces. No.
Yes, sir. Yes, sir.
And what is the function then?
Sir, it is f of t is equal to t, comma 3t,
F of t
comma
is equal to t, comma 3t,
comma 23 by 89t.
23 by
89t.
89t.
Yes.
Okay. So
I
is
have
this
done it this
function?
way.
Huh?
Uh,
So what
sir,
is the problem here?
Sir, I am able to solve it for 1-to-1. It is 1-to-1 because if I put t, it gives me, if I put t is equal to 0,
Okay.
then I put t 3t, comma 3t, comma 23 by 89t is equal to 0. And since it is in all in t, so this is equal to t equal to 0. So the t in domain and codomain is equal to 0. So it is 1-to-1.
Okay.
Regarding on to what I have made my reasoning, because there is no premise. Suppose I take a vector like 1, 0 and -1 codomain. I have no pre-image for this because the line in domain I have only one line. I don't have a three-dimensional space. Is it the right reasoning, sir?
Okay. Okay. So you are saying this is not a onto function.
Yes, sir.
This is 1 So actually, yeah, this is not a onto function. You can get a you can which element you are taking from R3?
Sir, 1, 0, -1.
1, 0, -1. Okay, so for this you are not getting a pre-image.
Yes, sir, because it is only a line.
Okay, this is only a line.
Other two dimensions.
Correct.
Is it the right reasoning, sir?
Yeah, actually this is correct because this represent a line in R3. This thing represent a line in R3. So yeah, like if you are let me tell you, suppose this is x, y, and z. So if you write the coordinates, it will be somewhere like this. So actually, if you see in R3, it will be a line in R3. So apart from this R3, if you take somewhere this element, this is belongs to R3. Okay.
Right, sir.
This is an element of R3. For this, you are unable to get a pre-image because elements, whatever the image you are getting on this line only. Okay. So that's why this is not onto. Yeah, this is 1-1. This is 1-1, but not onto. Yeah, it's correct. So let me tell you now. This is a specific example. Let me. What is the isomorphism? So see, you know what is the linear transformation? Linear transformation is nothing but a function, a specific function. The function is from vector space to vector space with these two property. If there is a function satisfying these two property, you will say this function is a linear transformation. Codomain and domains are vector space. Now, if this function have if this function is 1-1, if this linear transformation or this function is 1-1 and also onto, then we will say this linear transformation is an isomorphism from V to W. Means isomorphism, if someone says that F is an isomorphism from this vector space to this vector space, it means that this function is 1-1 onto. Or suppose somebody says this function is 1-1 and onto, so you can say this function is an isomorphism from V to W. So change the word, let's change the word function with the linear transformation. So what it means that if this linear transformation is 1-1 and onto both, means saying to bijective, then we can say this linear transformation is an isomorphism from a vector space V to vector space W. And in another word, or you can differently, you can say if this linear transformation is an isomorphism, so you can say this linear transformation is bijective, means to say 1 1 and onto both. So hope is it clear what is isomorphism?
Yes, sir. Yes, sir.
And what is 1 1 onto an
yes,
isomorphism?
Sir, clear till this point, sir. Suppose we have to check whether a function or transformation is 1 1. Do we always have to check for 0 0, sir?
Yeah, so yeah, actually this is one property of a linear transformation, that if suppose like there are two ways you can say. The basic property, as you know, that how to check a 1 1, saying to be like take a image like this, take two images. What is the basic way to check that? Let's say v1 is equal to f of v2. This, if this implies v1 is equal to v2, then we will say the function is 1 1. And for onto, take a element from the codomain, and if there exists an element from domain such that f of v is equal to w, then we will say this function is onto. This is the basic way. Like here, if you want to check this function is 1 1 or not, how we will check that? How we will check? Let's say t1 and t2 such that f of t1 is equal to f of t2, means t1 from this domain and t2 also from the domain with this property, right? So we want to check is this 1 1 or not. So then what will be the next step? We have this condition. So we have to reach at here. Like we have to show t1 equal to t2. If such thing is happening, then we will say, okay, this linear transformation is 1 1. So this ft1 implies that t1 comma 3t1 and 2 3 by 8 9 by t1. This is the image of this one. This is equal to image of the next one here. What will be t2, and this is 32, and this is 23 by 89 t2. So you have these two. So and now you know that if two vectors we want to compare, we will compare as a coordinate wise. So this implies t1 equal to t2. So what you get here, from here you reach that, yeah, t1 equal to t2 means the domain element. These are domain element. We took image element are equal implies domain element are equal. This means that as we know the definition, as we know the process to show a function is 1 1 or not. So this says that, yeah, this function or this linear transformation is 1 1. Now we want to check.
Still some doubt here, sir. Sir, actually the domain was f of t is equal to this.
Okay. What is doubt here?
Sir, it was from R to R3.
R to R3.
Sir, you have taken T1 to be in R3.
No, T1 is from R only. Domain. From domain I am taking. This is R only. This is from domain. This here. T1 from R, T2 from R. So what will be the now f of t1 and f of t2? This implies f of t1 is equal to this much as the definition of the function or linear transform. F of t is equal to this. This is.
Okay, sir.
Clear to all of you, know, or am I audible to all of you, or I don't
Sir,
know?
I have a doubt, sir. So we are saying it in terms of T1 and T2. So I was thinking if one of the points, suppose it was T, comma T square, comma 23 by 89 T. So if that was the case, how would we say that whether it's 1:1 or not? How would we say it in terms of T1 not equal to?
Yeah. So suppose the case is your function is defined like this. That's a line rest say it is here as it is. So your images will be like this. No? Now you got from here, you will get that this implies that T1 equal to T2, and also these two implies that if you compare if you just compare, this says that T1 is square is equal to T2 square, and also you will get 3T1 is equal to 3T2 means says T1 is equal to T2. And here also says this one also, if you compare, says T1 is equal to T2. See, this is not a linear transformation. First, let me tell you, if such cases happen, like whatever is, this is t square here. So if you check this one, let me make it bigger. If you check this property, the first one property only, you will see that it will not, this function will not satisfy this property. How? Because if you take, let's check that also, because how, see, if there is a function, how we will say this function is a linear transformation or not, or saying to be a linear mapping. Before to say linear transformation, if there is no word written that like this, suppose f is from a set V to W, a set, I'm saying a set, not a vector space. So V is a set, W is a set, and satisfying this property. So this is called linear mapping. It's equal to C time f of x. C time is equal to C time f of x. So this is called linear mapping from a set V to W. This set, if we replace with, if we will say this set forms a vector space, this is also vector space. So this function or this linear mapping, just call it a linear transformation. I hope you are getting what I'm saying. What is the differences, linear mapping and linear transformation? Only the wording have changed when the domain and codomain are shifted or maybe changed with the word vector space. That's all. Getting, everyone is getting what I'm saying?
Yes, sir. But both
Yes.
both the set V and W are in vector space.
If both the set are forms of vector space, then just change the word linear with the linear mapping to the linear transformation. That's all.
Yes, sir. We do the linear mapping in when we find the it's a 1-1 or onto.
No. This is not say 1-1 onto then linear mapping. No. Only if these two property hold, you can say this is a linear mapping from a set to this set. If this sets form a vector space over R, then you can say this linear mapping is a linear transformation. That's all.
But sir, here given R
Both
square.
the properties are compulsory to.
Yeah, actually, yeah, both this property is compulsory to say a function is a linear transformation, and means to domain is also compulsory to say domains are vector spaces. First to say domain and codomains are vector spaces, and with compulsory to these property, if these two property holds, then we will say that linear mapping is a linear transformation.
Sir, I have one specific doubt, sir.
What is that?
Sir, like the f of t is equal to t, 3t, 23 by 8090. Sir, when we are taking three coordinates, these are t, 3t, and 23 by 8090. How can it be in R only? The domain is R only when we are taking these three vectors.
Sir,
domain is written here R. That's why it is R. No, I didn't.
R square tends to R cube, sir. R square, R2 tends to R3.
It should be t is equal to t. How can sir three components be there in single R, sir? Because dimension of R is 1 and codomain's dimension is 3. R3 means here saying to the three coordinates.
Some point in the
that, like the function is saying, like we are transforming a single vector into a three-dimensional space. Is it what?
Yeah, from one dimension to we are transforming element to in 3 dimensions.
And we have to check whether it is a linear transformation or not.
What we are doing, what is the picture of this mapping is, suppose this is your real line and somewhere is your t here. So what here we are doing, there is a function which map to here in R3. Let's say this is x, y, and z. Map to here. So here, suppose here the t maps to here. So in this element will be in the coordinate, right? X,
we are checking whether we are going to three-dimensional space linearly or not.
So the question is we are shifting to here with the linearly or not? Linearly means with this property.
Okay, then we have to, in function definition, we have to then check whether what we input and what we get out.
Yes,
We
yes.
have we have to check for the pre-images. If they both satisfy, then we are going linearly. Otherwise, we are not going linearly.
Correct. Correct.
Getting
So is
sir,
this
can we take one or two more examples?
Yeah, yeah, I will take. So is via picture is clear to everyone?
Yes,
Yes.
Sir, you have explained one-to-one. How would we understand onto in this?
So actually this is not onto, so we will actually remain to check. Just one I just discussed.
Yes,
So
yes.
yeah, I will check for onto.
Sir, please take 2 or 3 more examples so that the concept is more clear.
Okay. So,
may I ask a question which is more fundamental?
Yeah.
One-on-one means necessarily that every element in domain will have a mapping to codomain, or can some things be left out in the codomain?
No. So actually, it's a definition of a function. No, you cannot left a single element in domain. Each have mapping to each element have mapped to here, because this is the definition of function.
Okay.
Then you will say, if suppose there is a left, then this is not a function itself. Then how you can say linear transformation or mapping?
So in onto you have fewer in the codomain than domain.
Yeah, if suppose for checking onto, there may be possibility that there are some element left in this codomain. Maybe it not map, it doesn't have pre-image. That's fine. But for each in domain, for each element there should be a mapping in the codomain. That's why the concept this concept comes, this onto concept. That's why we used to check, for each image we are getting, or each element for in this R3 we are getting a pre-image of here or not. If not, then this is a function but not onto function.
Okay.
It means that codomain and range should be same.
Can I have a moment, please? If I actually flip it, if I have more elements in codomain than in domain, and all the elements of codomain are not mapped to domain, that means there are some elements in codomain which are left out. Is it still
In such case, that function is not onto.
Because codomain should be equal
to. It's not a one-to-one. It's not a one-to-one.
It is not.
It may be one-to-one. It may be one-to-one. It may be one-to-one, but not onto.
Yeah.
It may be one-to-one.
One element of domain has only one on the codomain, but there are some elements of codomain left. It still can be called as one-to-one.
No, the condition is like that. Suppose this is not happening like this here, and suppose the image of this one also is the same here, then this is not 1-1.
That is onto. That is okay.
Yeah, in such case is not 1-1. If it is for each one differently, it is like that, then this is 1-1. But still it is remaining an element here which don't have image. Means we are not getting a single element which map to here. That means this is not onto. But if one by one differently we are getting image, so that in that case this function is 1-1.
Just to reiterate what you just say, what you said.
For each element you are getting different image every time. It is not the case like this. If it is not happening like this, then this is 1-1. If then this is not 1-1. If it is like this, like every time different you are getting, so in that case this is 1-1. But now the next is, suppose there is an element in R3. For that you are not getting a single element here which map to here. So in that case, if you are not getting, then it is not onto. Suppose for each element here you are getting a pre-image here. Pre-image means for each element here you are able to get an element here which map to here. If such case is happening, then it is onto. Okay.
So if a element in codomain does not have a pre-image, it is definitely not a onto, but it can still be a one-to-one.
Yeah. Okay. Yeah, there may be cases that it may be 1-1 but not onto. It may be onto but not 1-1, as your function as usual used to do in math 1. There may be possibilities which may be onto but not 1-1, maybe 1-1 but not onto. There are also 1-1 onto both. So there are these possibility as you used to do in the math 1 about the function. Here is also for the linear transformation, these things are also possible, because this is a function. But only with the specific property, that's all. These two, because of these two property you are saying. Otherwise, all property, whatever the function have, this linear transformation also have. And whatever the process you use to check for the 1, 1 and 2, the same process also applies to check 1, 1 and 2.
Okay. Thank you. Thank you.
Is it clear to all of you?
Sir, I have a question. I would have assumed that for linear mapping, we would not take values such as t1 squared and all that.
So yeah, if suppose such kind of thing is happening, then check your these properties. If
they are
this
being
property
fulfilled.
is happening, if suppose your t square is here, but still it is following like this, then you can say this is linear transformation. But it will not follow. It will, you know, that because of t square, what is happening? Let's check for this one. So what is, suppose your t square is here, then f of, let's say your x is t1 and y is t2, as your domain is, this function is from R. This means to vector space R to vector space R3. So your x is, we want to check this one. Okay. So is this satisfying or not? So your x is t1 because vectors are like the real numbers. Okay. So this is t2. Now what this implies, that what will the image then? As your function is defined,
f of
t1
t1
is equal to t square 3t and 23 by 89t. Your function is, we are supposing like this, it is defined. So it will be t1 plus t2 whole square 3 t1 plus t2, because as here is only single vector. No, now you are adding these two vectors. So this is, we have like this
23 by 60
18
t1 plus t2.
So your whole vector is this one. So now let's check the next one is, so
Distribute
you
over
need to, if
addition.
you expand, it will be t1 square plus t2 square plus 2 t1
t2
and this is t1 plus 3
t2
and this is
23 by
this,
69
and
t1 plus 23 by 69 t2
89 t2. So next is, if you try to make it separate, so t1 square 3t1 23 by 89 t1, let's make it one thing, plus t2 square 23 sorry, this is
3t2
3t2 and
23 by 89 t2.
89 t2.
So you are getting, you are not able to get this one. You are getting also, it is remain to add this to t1 t2
2 t1 t2. Yeah.
What somewhere. So not exactly.
Yeah, so this property will not hold.
Yeah, it is
the
exactly,
first
you are not
condition.
getting this property.
Yeah.
You are not able to get this one
No.
because of this new term. So in that case, this function is not a linear transformation. So that's the process you will use. You will use to check.
And it's most likely, if we do have some degree other than 1, it would probably not hold.
Yeah. If degree is, let's say, if any of any component is degree is greater than 1, it may not be a linear transformation.
Okay.
Will not be, I'm saying, because at this time, till now, this time I'm not getting such that it have more than degree. It may be linear transformation, but I am not sure, because change the vector spaces from real line to from different thing. From see, there are some vector spaces which is polynomial or matrices. So if in that case, it may be possible to a linear transformation. But for our course, we are dealing with the real line only. So for here, if square is there, then it will never be a linear transformation. For this course only, for this online degree, I'm saying.
But otherwise, the vector spaces could be in polynomial form also.
Yeah, because
not in the real line.
The vector spaces, there are possibility to be the linear transformation which have this more than degree, more than 1.
Thank you, sir.
Sir, can you do chapter wise?
Chapter wise means?
means what we have in the 5.1 like that.
Wait. Sir, can you take one or two more examples?
Yeah, we took from the linear transformation. Slowly we will back to the 5.1.5.5 lecture. There is no issue. As you are getting the this doubt, you can ask and we will deal with. This is the process. Otherwise, it will be like a teaching the lecture maybe. So,
sir, can you take one or two more examples, sir, please?
This is
So
going
how
good,
do
sir.
we check onto, sir? Onto function.
So let me back to check this onto. It's remain to check onto. So we are how to check again. So as you know, this is the process to check 1 1. Now let's check for onto. So our function is as here. Okay. Our function is f of t is equal to t 3t 23 by 89t. So this is our linear transformation from R to R3. We want to check is this onto or not. So how we will check this one. So if you let's take, I don't know which element need to take. I am just taking element randomly. I am choosing because or let's say okay, I am taking not randomly. I am taking a general vector itself. Let's take x1, x2, x3. This is an element of or a vector of R3. Okay, and we will try to find the pre-image of it. Okay, is there any t exist such that f of, or let's say with the word t, I am saying is there a element or a vector from domain exists, let's say yes, such that f of s is equal to x1, x2, x3. Okay, so I suppose that okay, there exists, I'm assuming we will reach to a contradiction. Okay, let there exist yes in the domain such that f of s is equal to this. So this implies yes 3 years and 23 by 89 yes is equal to x1, x2, x3. Now if you compare here, x1 is equal to yes, x2 is equal to
3s.
3 years. So I am removing it here with the okay, x2 is equal to 3 years. This implies
s is equal to x2 by 3.
s is equal to x2 by 3. Okay, now x3 is equal to 23 by 89
s.
Let's say s is equal to
89 by 23 s x3.
So we get, see that this is one, this is one, this is one. So all are, see, you are able to say right side or maybe this side, these are the equal. So you will write it like this: x1
is equal to x2 by 3 is equal to 16
by
23 x3.
So if you have an element or vector satisfying this, then possibility that yes is exist, right? Otherwise, let's say I am taking now which is not satisfying this, or let's say I am taking like this. Now we can take, see, we generalize it. Now let's take x1 is equal to 1, 0 and 0. Let's say x1 is equal to 1, x2 is equal to this one, and this is okay. Now substitute here. What implies here? I am saying here yes is equal to 1. This implies yes is equal to 0. So what you are reaching, you are getting a contradiction. What? 1 is equal to 0. So this is absurd, right? This we are getting. We took a vector 1 0 0 and we got that 1 is equal to 0. So what it says, we assume, our assumption is wrong. What we assume, that
assumption is wrong.
there exists yes such that this is satisfying, but our assumption is wrong. Because of that we are reaching here 1 is equal to 0. So this says that this function cannot be onto. If it is onto, then we will surely get yes, but we are not getting yes. If you are assuming it, we are reaching a contradiction. Is it clear to all of you what I'm saying?
Sir, that
Yes,
means
yes,
the
sir.
whole vector space R3 is not the range of this particular
So whole
function.
vector is not in the range of this function. Means to say this vector is, now let's see geometrically what it means. That now actually what is this, the linear transformation? This linear transformation in geometrically it says that we are mapping, this is from R to R3, this is T, it maps to, actually this linear transformation is a represent a line on here somewhere like this. Maybe it may up and down, whatever will be. If you this maps to on a real line, means if you suppose this maps to here, this maps to here like this, you are getting. If you take an element from here, then you don't have a pre-image. If you take image here, then you have a pre-image. But if you will take if you take an element from here, from this R3, you don't have an image because all maps to on this line. This is the actual meaning of this linear transformation is happening. Is it clear to all of you?
Yes, sir.
So
the
could you
graph
also
is not this graphically it is not clear. How the
Graphically means if you are not getting what is happening, because how I am saying this is a line, this is a more when you learn this in week 9, 10 and 11.
Okay, you mean to say that if we put one value, suppose 1 in this function, we are getting two different values, which is not possible. 1 and 0 at the same time is not possible.
You are taking an element. If you are taking a vector like this 1 0 0, you are getting absurd. Means we suppose we assume that this function is onto, but when we check that it is onto or not with an element, we are reaching as a absurdity at absurdity.
Right, sir.
Okay. If you want to see
means there is one there in codomain there is one element which does not have a pre-image. At least one.
That's the means that you have an element 1 0 0, not only one, infinitely many elements. As an example, I am taking 1 0 0.
Yes,
There
yes.
are infinitely
There could be many more.
There could be many elements which don't have pre-image. Okay. So
Yes.
actually, how it is representing a line, you can see in GeoGebra easily. Let me tell you how it is. Why I am saying the line.
Sir, while putting the equation GeoGebra, kindly guide also, sir. I don't know how to use this.
Okay, so so what is happening here? You just write that image. What you got? I am changing t with the x, or maybe let's say t is also will work here. T and 3t and 23 by 89
t.
So actually, those if you collect those vector, it says actually if you are changing t with the line here, changing t uh, with the real number. T means t are real number, so you are changing 0 1 1 whatever you are getting. Just collect those coordinate. You will see that actually this image is actually represent a line in R3. This is a line in R3.
Yes, sir. It's visible, sir. Now it is visible.
So as I made here, actually it will pass through origin. It will pass through origin because that is a linear transformation, and linear transformation has property that if you are making, I made a mistake in the making the picture pass through origin.
Vector space thing.
Actually,
yes, because it is a vector space, it has to pass through region.
No, because why? Every linear transformation, image of zero vector is 0. For every linear transformation, image of zero vector is 0. If suppose this is a linear transformation from a vector space V to W, so image of zero vector is actually says to be 0. So when you will add 0, it will give your image 0. So
You
that's
mean to
why
say
it
that
passes.
0? You mean to say, sir, that 0 in vector V is transformed to 0 in vector W?
0 vector in W. 0 means here is this is 0 vector in W. This is 0 vector in V.
Right.
So because of that, it will pass through this. If you have a suppose somebody says that somebody graphically asking that is that linear transformation like that he is making. Suppose he says that this is the linear transformation and are mapping to here this line. So this will never be a linear transformation because of this property, because it is not passing through origin. It should pass through origin. Then you can say this map is actually a linear transformation, and the reason is because of this property. So that is when you will do the next week. That is linear transformation matrix representation.
Okay, no problem. Sir, can you take one more example?
Yeah. So
I just one question. This is for linear mapping, this 0, 1, or it's also for it's for linear transformation only, or also for linear mapping?
No, for linear mapping it will not work. For linear transformation it will work, because
so it's a condition for linear transformation. The 0,
it is the condition for linear transformation, because
but not for mapping.
There may be mapping. Mapping is just a mapping. Linear mapping is just a mapping on from a set to set, not saying to a vector space. When we are changing the vector space word, it consumes. That's why we are studying also. It have so much qualities. Like it have. This is the vector is like linear algebra is totally depend on linear transformation. When you go with the next week or maybe ahead course, when you read this linear algebra course, when you do it properly, the whole thing is totally depend on linear transformation. It has so many properties. Not only these are the single properties are here. Isomorphism 1 and 2. This is map to 0. Eigenvalue, eigenvector, matrices. All matrices are derived from this linear transformation. Actually, there is a property that for every linear transformation you will get a matrix. For every matrix you will get a linear transformation. So every matrix, whatever in this world have, can be transformed to as a function. Means linear transformation. In this real line, I'm saying real R3 to R2, R2, whatever have. It have so many properties, linear transformation. That's why we are studying also.
Sir, if we where is this? Where do we use this concept of vectors practically in real life problems? Where is this concept used, sir? In industry or?
Yeah. So when you come into MLF, machine learning foundation, then you will say better way, full of maps to application. When you will know the eigenvalue, eigenvector, then you will realize that okay, whatever you are studying here, those things will work to in the MLF. Till now here you are not able to see, but when you come to MLF,
yes,
you
sir.
will see. Okay. So hope all of you got the idea how to check 1 and how to check onto what is the linear transformation, what is happening, how we will check a mapping is a linear transformation or not, and what is 1 onto, how we will check.
Sir,
the same process.
Can you take one more example, sir, so that it is more clear?
Okay. So yeah, I will take that example. Okay. But is it clear to all of you what till now what I have discussed, or all of you have just discussed?
Yes, sir. Clear.
If you have a doubt, you can stop me and I can ask, because now I'm going to change with the different example also, and maybe I take some like anyone have doubt in the activity or practice, you can ask here itself. Then we will discuss with the new example.
Sir, it's becoming more clear now only, and I'm now thinking if it's from R to R3, R is domain and R3 is codomain. Most likely onto function will be hard to meet depending on how the function is defined, but because it's going from a single value to multiple in R3, so it onto will become difficult, no, unless it's a specific function.
Okay, so I am telling a trick. Maybe it will help to all of you. Like it to how when we will say a function is probably just looking but the condition is it should be the vector spaces should be R or R2 or R3 or Rn also. Vector spaces should be Rn, and I am restricting to here till to this one, and the property is that suppose this is happening from Rn to Rm, but the condition is m is greater than n. In that case, this linear transformation may be 1 1, may not also, but it will never onto.
Yeah, when you showed visually, it started to make that concept clear, that it's hard to meet the onto. Yeah, as you said, not onto. Correct. Thanks.
So actually, you can see the reason also. You can check with this one. Actually, our previous one map is from R to R3. So see that this is m is greater than this and 1. This is 1 here. This is 3. So 3 is greater than 1. If such thing is happening, then it will never onto. It may be 1 1 1, as we just now checked that. Yeah, the previous one example is 1 1, but it will never onto for such cases.
Only if the function is defined very narrowly. If it is defined, for example, t comma t comma t, so then would it be onto, sir?
T comma t comma t still not onto. No, still your map is from R to R3.
Yes, sir.
Still your map is from R to R3. So
but for
I'm saying
every
for general case I am saying, suppose still this is 1, this is 3. So as here I am making condition m is greater than n.
Yes, sir.
Strictly greater than, not equal to also, strictly greater than. In that case, it will never onto. And actually this can be proved, and this we will prove in the next week.
Okay,
sir. You will know with the rank and nullity theorem for the linear transformation, then we will easily can prove.
Okay, sir.
Can I ask a question on the same thing? If it is t square, what would be the value of t in the first function? Like let's say r in the domain r, if I give t, and I said t square, t, even if it is positive or negative, it can yield to the same set of values in R3, isn't it?
So for which context you are checking? Because this is not a linear transformation.
Yeah.
Okay.
There it will fail. Yeah.
So no need to check, because for this course, if such thing is happening, then the question will be like, if this function is linear transformation, then it is 1 1 onto, he will like this, he will ask. So what is that? You need to check first if this linear transformation or not. If it is failed, then you can directly say this option is not true. So the condition is first check that it is a linear transformation, then check 1 1 onto. For this course, I'm saying.
Okay, thank you.
So, sir, whenever the values in square or something, so then it is always not in linear transformation.
No, sorry. Can you repeat again, please?
When the values are in t square like that, so we say
then you
that
can say for this course you can say those things will never, or not only t square. Let me tell you also, if it is like this, ax plus b, or maybe like this,
yes,
a t plus b, or or t square, or any power is happening, or it is like this, t square plus t plus 1, means to say if it is not only added a single constant also, then it will also not a linear transformation. I mean to say, suppose your map is from R2 to now let's change with this R to R3. Let's change the context with f is from R to R3. I am saying now your I am defining this like this, f of image of a vector. So in this I am taking a vector v from R2. So it will be how it will be look like x1 and x2. So image of v means writing to x1 and x2. If you are again extra need to bracket you want to add, you can add, otherwise just you can remove. So image of this vector means this is, and it is like this, f of a, or no, sorry, ax1 plus b, cx2 plus d. If this kind of, so it means to say, see, this is the relation, sorry, this is from R3, so I need to extend it, because in R3 the element will be x1, x2 and x3. According to the element we need to go. So let's add this e x1, any like I'm making the this function, so I can make it 1 or 2 also, whatever, and this is ef, or let's say I'm erasing that sub, this is the only, this is the case ex1. So in such cases this will never be a linear transformation because of this constant term. Actually you can check this one.
Yes, sir. It does not satisfy the property of ease
or not. It will fail because of this constant term.
Yes.
And now I'm taking another linear transformation.
Sir,
now
could you repeat that part about the constant?
This, because of this constant term, this property will not hold. So okay, if you have confusion, I'm changing with this 3 and with the real numbers I am making it. This is 1 here, so let's take this is 2 here and this is 1, no matter. So our function, our linear transform, so this is not, we will say linear transform, let's say this is a function. We want to check is this function is a linear transformation or not. So let's take 2 vector v1 and v2. So let's check this is x1 and x2 and this is y1 and y2. So f of v1 plus v2, it will be x1 x2 plus y1 y2, right? So yes. Next term is, it will be, now this is a single vector, so let's add it because 2 vectors are added here, so it will represent a single vector. So it will be x1 plus y1, x2 plus y. So this is a single vector. Now it is defined like this. So
there is a noise. Can you mute all?
Let me mute to all. Okay, I muted to all. Okay, so now our function is defined like this. So this is 3
x1 plus y1
plus y1, because this is the only one component. No, this is one component, this is another component. Yes. So this is
plus 1
and this is the for x2 here. Well, it will work plus 2 and the next one is x1, so means this one
x1 plus y1
plus. Also maybe you are not confusing with the this thing. No, I am making a very clear. Okay, I'm thinking there is no confusion with the more time x1 x2. Yeah, it is okay because yeah, I took x1 y1. Okay, so this is correct. So I means to say distinct notation. So this is now 3x1 plus 3y1 plus 1, x2 plus y2 plus 2, x1 plus y1. So we have this one. Now I am trying to make it like this because we want to be here, it should be like this. If this is happening, then we will say it is a linear transformation. Otherwise this will not a linear transformation. So we are able to make it here or not. So it will be 3x1 plus x1. What we can do, 3x1
plus x1.
You are adding 1 here. Okay, so and this is x2 and this is x1 in one bracket, in another bracket 3y1 and
y1. y1.
This is
y1 only. y2
will be na. Oh, sorry.
It will be 3y1 plus 1. 3y1 plus 1. 3y1 plus 1.
No, 3y1
plus 1.
Oh, sorry. Here is okay. Oh, sorry.
We have already done 3x1 plus 1, na?
3y1 plus
1.
Okay, 3. No, what is that here?
We have already done 3x1 plus 1.
I'm taking this one and I'm taking this one, y2 plus 2 and this one.
y1.
Oh, sorry. This is No, I made a mistake.
Oh,
I
we're
think. Okay,
expanding that
correct,
right
correct.
hand side.
It is correct? No, it is correct. Yeah, it is correct as our this one. Yeah, actually, so what is the, yeah, it is correct. So what is the condition here? We are not getting here 1 plus 1, or we are not getting here as our previous, as our, we are not getting our mapping, exact mapping, this one.
Yes.
For
So
this
it is
one and for
one.
this one. Problem is this here. No, this is not exactly equal to f of x1 x2. This is not exactly f of y1 y2. Okay, not exactly, because I needed 1 here, there is not 1. I needed 2 here, but there is not 2. So this is failed to making like this. So in that case, this is not a linear transformation. If suppose it is like this, I erased here 1, I erased here 2 here, and this your mapping is like this. So the next, let's go with the 1 by 1 here. We will reach to here. Okay, now let's erase this one, let's erase this one. So you'll here.
Every time when you give this type of question is coming to be solved, that's way as you
Yeah,
said.
yeah, every time you have to, then how you will check if you are not do like this? It's difficult to check that, no?
Yes.
So now make it separately. Now 3x1 x2 x1 and plus 3y1 y2
y1,
and this is exactly equal to x1 x2 and plus f of y1 y2. So this follows. Yeah, see, one thing we checked only one, still remain to check this one, no? This
Yes.
c times v. So let's check this one also. Sometime this is correct, okay, for a particular, but this may not also true. So you need to check both. So next is remain, we have to check actually. So we assumed v is equal to x1 x2. So f of c time x1 x2. So this is equal to f of cx1 cx2, and this is our defined function is 3x1. So 3cx1, and the next is cx2 and cx1. Our function is defined like this as above. So this is you see, c is, you can make it out here. So 3x1 x2
x1,
and this is c time or exact f of x1 x2. So both condition you have to check, then now you can say here this our linear transformation is sorry, our function is linear transformation. Otherwise no, both conditions should follow. Let me make it smaller. Okay. So I hope to checking how a function is linear transformation or not. Is it clear to all of you? So
yes.
Now
then we check the it is 1 1 or 1 2.
So you can check is this 1 1 or not, 1 1 on 2 or not. So if you want to check this is 1 1 or not, so same thing, what you will do, let's take there exist our function is from R2 to R3. Okay, so let's take two vector from domain. Let's say I am taking v1 and v2 from R2 such that f of v1 equal to f of v2. Okay, if this we have this one, okay, such that this, now assume v1 is equal to x1 x2, v2 is equal to
y1 y2.
y2. So we want to reach here v1 is equal to v2. We want to reach here. So as we assumed this is equal to this, so our function is defined like this will be x1, x2, and this is equal to y1, y2. So next is, as our function is defined, this one, for example, we are taking this. So this is 3x1, x2, and x1. X2 and x1, and this is 3y1, y2, and
y1.
y1. Now compare it. So this is 3x1 is equal to 3y1.
3y1.
X2 is equal to y2, and next one is itself implies
x1 is equal to y1.
So what it means that x1, x2 equal to, as here we are getting y1, y2. So final thing you got right, v1 equal to v2. So actually this linear transformation is 1, 1. Now need to check onto. So if you want to check, let's check onto also. If onto is difficult to check, I'm again saying this will assume this linear transformation is not onto, because just now if you are taking my trick which I just now told you,
m greater than m, then not onto.
M is greater than m, so it will never onto. So this is 3 and this is 2 here, so it will never onto. So let's check with the as usual algebraic way. So I am assuming, assume this is onto. So it means there is a vector, let's say
v1.
Let's take a vector x1, x2, x3 from R3. This is a vector from R3,
which is the element of R1.
No. So your
just an image in R1.
So there exists a vector in R2. Let's say
R2. Yes, sir.
Assuming
x1, x2.
x1, x2 will mix here. So I'm assuming here alpha beta from vector R2 such that f of alpha beta equal to
f of
x1, x2,
x3. So f of alpha beta is equal to 3 alpha beta, here is alpha only, and alpha. This is the definition. This is equal to x1, x2, x3. Okay. If you compare here, so
3 alpha is equal to
3 alpha,
beta is equal to x2,
beta is equal to x2,
and alpha is equal to x3,
and alpha is equal to x3. So
contradictory.
We are getting
alpha is equal to x3 and x1 by 3 both.
So yeah, we are getting here. So x1, or let's make it 3
alpha is
equal to x1. So alpha is here, alpha is here. So
alpha
assume,
is equal to,
let's take a vector to check that is okay. Let's check 1, 1, 1 itself, assuming x1 is equal to 1, this one is equal to 1, this one is equal to 1, 1. Because this is a vector of R3, 1, 1, 1. This is a vector in R3. So what is happening here? Let's substitute here.
3
so
alpha is equal to 1.
3 alpha is equal to 1. And
beta
here alpha is equal to 1, beta is equal to also 1.
1.
So what it means that alpha is equal to 1 by 3 and here alpha is equal to 1. We are getting. So means 1 by 3 is equal to 1. Which should never happen. It will never happen. So that means you are assuming, you are reaching at a contradiction. And this says that your function is not onto. And our trick is also going to be true here.
True.
So does the trick works other way around? Like if we say we are transforming from say sir, R2 to R.
R2 to R. Okay.
Yes, sir. And we are checking onto, then it cannot be onto.
No,
then it cannot be 1, 1.
So let me tell you, if you told here, so let me again extra trick is here. If you suppose your linear transformation from Rn to Rm, okay,
and m is smaller than n.
Actually, this says that it will never onto. It will never onto, but maybe 1, 1. Now, see, it will tell you a very interesting thing. It will different way. It will never 1, 1. Never.
Yes, sir.
Never 1, 1. But it
could be onto.
Sir, m is greater than n in this case also.
M
Sorry.
M is not greater than n is greater than
the
m.
condition here I didn't put here. So n is greater than. See, you will see these things in next week, means maybe in video lecture you will not see, but when you come to know with the this rank nullity theorem, you will very easily prove these all very easily. But till here for this, for the week
tutorial, sir, last tutorial question, same question they have discussed.
regarding this one.
Yeah, sir.
Okay.
And for the 1 vector, they have taken rank and nullity concept, 1 1 and on to.
Okay.
I didn't understand, sir. Why they have taken rank and nullity for checking 1 1 and onto functions?
For week 6, we are saying.
Okay. So there is.
So if you come to week 6, then your matrix can be converted as a matrix. Sorry, your linear transformation can be converted as a matrix, and then rank nullity will work there.
Okay.
Excuse me, but rank nullity is already discussed in week 5.
So let me tell you the differences also. You asked here, so let me tell the differences. This rank nullity theorem is for matrix. For matrix, this rank nullity theorem. In week 6, you will see rank nullity theorem for linear transformation. So there are two different rank nullity theorem. In this week 5, you have rank nullity for matrix, and in week 6, rank nullity theorem for linear transformation. So please be clear with these two. Okay, so I hope at least linear transformation is clear to all of you. So if you are not asking the question, I have my question with the this one.
Can I interrupt once again, please? Okay. If you don't mind, can you explain the onto example once again, the one that you just solved?
Okay.
Yeah.
Okay. So what we did here, where is that? Okay, here. Okay. So what is the process to check onto is what onto the definition for onto, or what is the condition a function is onto. Suppose you have you can tell. Then if suppose you have okay, let me tell. Suppose your function I am saying okay, from a set S to T. So this function is said to be onto if
all
for
the
each
elements.
element of T, let's say I am W, I'm taking an element T here from this. For each element of codomain, there should be an element in this domain. Let's say A I am making here, such that f of A is equal to T. This is the definition for onto. So what I did here, I assumed a vector, let's say x1, x2, x3. This is a single vector in R3. I assume that okay, this function is onto. So the process is, I assume there is a vector in R3. I assumed a vector in R3, and there exists a vector in R2 because your domain is R2. Our function is from R2 to R3. So I took a vector, general vector x1, x2, x3 from codomain, and I assumed there exists a vector alpha, beta in this codomain. Means this is a single vector. There exists a vector in domain such that f of alpha, beta equal to this
x1, x2, x3.
x3. This is as definition says. Okay. So, is it clear now?
Yes, so far, yes.
Yes.
Okay.
Sir.
So now, as definition of the linear transformation is, I just
we will do addition
here. I just split it here, and when these two vectors are equal, I just compared these two vectors, and I got 3 alpha is equal to x1, beta is equal to x2, and x is equal to, because of if we compared with this. Okay. So we got these three equations. Okay. Now, because these are the general elements, unable to say that okay, happening or not. So for example, let's take a vector 1 1 1. I took just a vector, means to say let's give the value to x1 x2 x3 is 1 1 1, means to say I just given to the value x1 is equal to 1, x2 is equal to 1 also, x3 is equal to 1 also. So I just and put it in the equation whatever we got from the here, and we reached to here, and when we solve this equation we got a contradiction. So
Sir, every time we give the value of x1, x2, x3 for checking,
not
always
one
give
one, any for example, see, I luckily got this one. Otherwise, maybe if you are like not lucky, then you may got like satisfying this equation. Maybe you will reach to a satisfying equation, but I luckily got this one. Maybe if my luck is bad, then maybe I got what will be the here then the proper thing. Suppose I satisfying
One,
this
1 by 3.
1
One,
1.
no, sorry, 1 by 3, 1 1.
Okay, 1 by 3
1
1
1.
1. If I suppose badly I took this one, then it will be 1 by 3. X1 is equal to 1 by 3, and this is 1 1. So yeah, actually it says alpha is equal to 1. So
Yes.
and satisfying the equation. So if you are lucky, okay. Otherwise, see, these things can be actually when you do more practice, you can easily. I am not saying the lucky. See, I did this course, so I know maybe this will help. When you do practice, you will easily get okay. This can never be untook. Okay, so far, don't worry with that. If you do more practice, you will get.
So every time we check the n is greater or R2, R3,
For the trick, you can take. That's why I just given the trick.
So the idea is to negate the assumption, is it? We start with
So
saying
actually we assumed and we reached the contradiction, so our assumption is wrong.
Okay, thank you.
So in the examination, when the hurry we do trick, always apply trick, or we do solve
so the thing is, if you do more practice, you will get more tricks yourself, and then apply those tricks. That's the good way, I will say. If you do more practice, you will get more tricks for your own, not only whatever I given, your own tricks you will get, and just you can using those tricks you can neglect.
But sometimes we say that we might find its assumption maybe, or
actually, that's why that's the thing. If you are not lucky, then you will take a wrong assumption, and okay, you will say okay.
So we can do it like, we take two assumptions, because there is R3, then we can do two values.
So if you are getting this one, so take another vector also 1 2 3 or 1 0 0. Take a easy vectors and quickly check. I mean to say 0 1 or -1 0 0. Take a easy vectors like 1 0 around to 0. I mean to say take around to 0 vectors. Those are the easily you can check, and take the integers, whatever the coordinates, take integer and quickly check.
Okay, sir. Matlab means 2 or more integers.
Around the 0 and take the integers number, so that you can easily check and will not take time. Very quickly you can do.
Yes. So this shortcut method where m is greater than n or m is less than n, it's just for checking isomorphisms, right? Not for linear transformations.
No, checking for isomorphism is checking for 1 1 and 2. 1 1 and 2. Actually, if this is not 1 1 and 2, so you will directly say this will never, or mean to say if these things is happening, so these types of linear transformation will never
Isomorphism.
See, the thing is why I am saying, actually I am let me mute to all of you, because just make it to all. So what is the reason behind it is, suppose you have a linear transformation from V to W, where V have dimension m and W have dimension also m. Here the word came because of these things are happening because of dimension. If both
Yes.
vector spaces have same dimension, so it is
Yes.
it is possibility that these two are maybe isomorphic. And if dimensions are differ, then the possible those linear transformation will never isomorphism. Okay.
So in a way, this is a very clear picture that they should be of the same dimension.
If both have same dimension, then
there'll be an isomorphism.
Not only there, actually the COT says there exists an isomorphism, or these two vector spaces are isomorphic to each other. So you will know more in the week 6. So please wait till week 6.
Would it be always be there, sir?
No.
Always be true that if M is equal to M, then it would always
maybe chances are there.
No. So that's why I'm saying isomorphic. Not I'm saying isomorphism. Isomorphic word I just used. So actually, if two vector spaces are like this, having same dimension, so these two vector spaces are isomorphic, means to say there exists a linear transformation, existence of a linear transformation such that this is going to be bijective. Okay, not saying if you have a linear transformation V to W where this have dimension M, both have dimension M, and the expression is given to you, and directly you will say it will be 1, 1, and 2. No, never. It says there exist, not for every. It says it give the existence word. There exists.
If it is bijective, then there has to be a linear transformation between two vector spaces.
Mm-hmm. So please wait for week till now. Week 6 is released. So if you do more practice, you will get all these slowly. We will discuss those.
So just to be clear, we are saying if they are not, the dimensions are not equal, they'll definitely not be isomorphic. But then if they are equal, will they be definitely isomorphic?
No. Maybe.
No. Actually, definitely isomorphic means to say there exists a linear transformation. Those are surely isomorphic, but this theorem is not proved in this lecture.
No. There is one writer that two vector spaces having same dimension are isomorphic if there is a linear transformation.
Actually, isomorphic dimensions vector spaces gives the existence of a linear transformation.
Yes.
So you will see that. Don't worry. So don't worry. That's why I was not trying to discuss this thing, because you may get confusion with the 1, 1 and 2.
It is clear, sir. It is clear.
Okay. Please watch the video lecture of week 6, then you will get a better idea. Okay. So if you are not asking, let's do with this this question.
Sorry, sir. In Reflect With Us assignment for week 5, there is a matrix form discussed, and related to that, if the determinant of the matrix that is formed, it's mentioned, it can be decided whether it's onto or not. Sir, is it possible to discuss that in Reflect With Us below?
Okay.
Last part of this.
Okay.
So last line, concluding from this, we can say if determinant A is non-zero, then T is onto.
So as our linear transformation is defined like A matrix and V. So actually this tells, please read one by one, because this is a very precisely written. Very precise. Because one by one, why this word is came, then it is going to be, what is that? Concluding from this, we can say if determinant, then T is onto. Okay.
Yes, sir. This is. I have
So,
also doubt for this. Why T is onto when determinant is not equal to?
Okay.
Think it's like a system of equations. You will get the answer.
Okay. So if you have doubt, the question is actually, the reason is our linear transformation is defined T of V is equal to AV. So just now we know that a linear transformation from V to W is 1, 1 if assuming to say v1, v2 such that T of v1 is equal to T of v2 implies v1 is equal to v2. If these things is happening, so actually these things also infer a property of linear transformation, that if your linear transformation is, suppose if you are taking v, means if the property is I am taking T of v is equal to 0, this implies v is equal to 0, then this is 1 1. This linear transformation is 1 1.
Yes, sir. That's there in one of the steps.
I think in this is in video lecture also. No.
Okay.
Actually, sir have I think sir have told this. If such thing is happening, what is that? If you have a linear transformation from v to w, and v is a general vector from this v with the property as T of v is equal to with the condition that such that T of v is equal to 0. If this implies v is equal to 0, then T is 1 1. Actually, this is a condition if and only if this is happening, this is true, and if this is happening, this is also true. So if you are checking with this way, also work. If you are checking with this way, will also work to check this linear transformation is 1 1 or not. Actually, if you want to, if we want to see it here, we can do for this question. If you if quickly we can do.
Yes, sir. Yes, sir. Please.
Yes, sir.
Okay, so our linear transformation is previous one is like that, like this, from f r2 to r3 is like this. Sorry, this is equal to 3x1, x2, and x1. So this is our linear transformation. Okay, so I assumed what is I assumed? F of v is equal to 0, where v is a vector x1 x2, okay, such that f of x1 x2 means here this is equal to 0. Okay, I assume this one, and if we got this implies that v is equal to 0 means x1 and x2 is equal to 0, then we are done. 0 means 0 0, here 0 means 0 0 0. Okay, because 0 vector will come in r3. So we want to reach here. Here is also it is okay. So if I assume this one, if I reach to here, then done. So I assumed, let's say f of v is equal to 0, where f of v means x1 x2 is equal to 0. So our image is says 3x1 x2 and x1. This is equal to 0 means here 0 0 0, because our image is, our map is from r2 to r3. So 0 vector in r3 is 0 0 0. So here 0 means 3 times 0. Now if you compare, what you will get? x1 is equal to 0, x2 is equal to 0, right? So that means you just assumed here and you reached here. This says that v equal to 0. No, v means here v is our x1 x2. 0 means 0 0. So we assumed here and we reached that okay, our v is 0. This also says our linear transformation is 1 1. This is also a way to check our linear transformation is 1 1 or not. Is it clear to all of you?
So then that means if it was we are because reflect with us is taking it in terms of determinant now, so it would be a square matrix. That would mean that r2 to r2 or r3 to r3 would be the only case in those cases. So in those cases, when we have a determinant as non-zero, then which means we are proving it this only, then it would be t's onto. This is what you're trying to say, no, sir?
No, not on to 1 1 1 1 for 1 1.
1 1.
1 1.
Sorry. Yeah, 1 1. Right. Okay. So to make it in terms of determinant, it has to be a square matrix, which has to be in terms of r2 to r2 or r3 to rn to rn, right, sir? Otherwise, a matrix or a determinant case will not come there.
No. So let me now. Just now we got. Is it clear to check that this is 1 1 or not? So
yes,
let's
sir.
back to our reflect with us. Why this needed? So why this infers that if determinant is not equal to 0, then that is onto he's saying. Oh, onto or 1-1?
The last line is onto, but before that, the case that you've described, v is equal to 0, that one is in step earlier step. So it's there.
Okay. This is he checked for he checked for,
step 3, I think. Step 3, step 4.
In last he concluded, if concluded from this way, is that if determinant answer, then T is onto.
Yeah. Okay. How I'm trying to relate it is that why it's coming in terms of determinant here is because they converted equation to matrix, which is only possible if it was same Rn to Rn. Otherwise, it wouldn't be possible, no?
Rn to Rn square matrix.
Yeah.
No. So actually, that is okay. If it is from Rn to Rn, that function is 1-1, then that is onto. If a linear transformation is from Rn to Rn, which is 1-1, this implies that this linear transformation is onto also. This is a condition. This is one another property. If you want to say, this is the third property. If a linear transformation from both have n dimension, then if it is 1-1, then onto also.
Yeah.
So,
and only in these cases there can be a determinant.
So actually what is happening here for our linear transformation for this reflective mixer, T of V is equal to given AV, and A is some matrix and V is your x1, x2. So what it says that T is from R2 to R2, but we will not use this one because this is just now I told. Otherwise, without using this one, we need to prove. So need to prove that it is one onto or not. So how it is happening? Let me explain you. So our T of V is equal to our linear transformation is this one, and we want to prove this is onto or not. Okay. So what it means, what it says, our this is T from R2 to R2. We want to prove this is onto or not. So let's take a vector from this from the codomain. Let's say I am taking V prime, or let's say W I am taking. Okay, from codomain I am taking W. Okay, so and I assume that same process we will do. I assume, okay, there exists element in domain. Let's say AB. AB means, let's say V I am saying, and we will change it to in matrix form. So, okay, or in the x1, x2. So there exists V such that f of V is, or f not, or not, this is not our f, this is T of V is equal to W, and T of V is actually our AV. AV is equal to W. Till now it is clear? Now
yes,
W is our R2. Element of R2 means it will be x1 and x2 type. Okay.
2 elements.
And V is also from R2. It will be a type of Y. Let's say I'm take Y1 and Y2 type. Okay. Now it is a matrix multiplication. So mean to say we can write this vector as also like this. No, we can in the vertical form we can also write, or this horizontally we can also write, vertically we can also write how we want. So it means A Y1 Y2 is equal to x1 x2. So our V is our Y1 Y2. Maybe
okay, got it, sir. Yeah.
Okay,
So
clear.
A also,
just variable differences. Okay.
A is also told in terms of the matrix form. So A is
so
ABC.
A is our, let's say I am writing like this.
Sure,
okay.
Sir.
Now
matrix multiplication is there.
This is a system of linear equation. No, this is a system of linear equation, and actually we are trying to find y1 y2. No, we are from here we are trying to find V, means trying to find y1 y2. And when this is a kind of system of linear equation, and
that's why it's saying that data should not be equal to 0.
So when this system has solution, if this matrix have determinant non-zero, that means this is invertible.
Then only it is invertible.
Then when then it is invertible. If suppose this is invertible, so you can multiply the inverse both sides. Means y1, y2 is equal to A inverse, which is a matrix x1, x2. What it says, you are able to find y1, y2 with this assuming to x1, x2. Getting no?
Yeah.
What I'm
So
saying?
okay. So sure.
That means you assumed a vector from R2, and you are assumed okay there exists y1, y2, okay, and when we solve we are able to get exactly y1, y2. How? A inverse time that whatever your x1, x2 is there.
I guess A is a square matrix.
Actually A is a square matrix, then it will be, then we are talking the determinant, no?
Yeah.
So got why it is onto, how it is happening, why the determinant not equal to 0 says this is onto.
So unique solution would be
It's a unique solution, correct?
Yeah.
Gives
There exists y1 and y2. That was our assumption.
This says there exists y1, y2, correct?
And our assumption is correct, hence.
Our assumption is correct.
And unique solution makes it onto.
Makes it onto. Unique means unique says onto.
Got
is it clear?
Now it's very clear. Thank you, sir.
Can you repeat the last part, please? Can you repeat the last part? Why is it a unique solution onto and not one-to-one?
Why it is unique solution? Because your determinant on 0.
Determinant
and whenever you have a system of
I can invert the matrix and I have either a unique or a multiple.
Actually, determinant in non-zero, you can invert the matrix as just now I inverted, I just multiplied and I got the value y1, y2 as whatever. The general case we are dealing with, the general case.
Yes. So
Clear?
how is that two elements of the codomain are mapped to one? Or rather, one element of codomain is mapped to 2 in the domain.
We are already done with 1, we are checking on 2.
No, I didn't your question. One
onto means we have one element of codomain has 2 elements in is mapped to 2 elements in the domain, or rather the opposite.
One element for codomain there should be an element.
One element in domain.
This is an element. Yeah, the thing is coordinate wise these are. Because of this you are getting confusion, or I don't know.
No, when we were discussing about whether it is one-on-one or onto, the clarification that was given is.
Oh, for one you are saying.
No,
okay.
no. For onto. Let me complete. Maybe I can correct my understanding of onto also. Onto means there could be an element in codomain which has which is mapped onto, or rather, 2 elements of domain are mapped onto 1 element of codomain.
No.
No.
Think it like that. All the elements of codomain is mapped to a domain element.
All elements of codomain, nothing is left out, and they are mapped to the codomain.
Nothing is left out in the codomain. Yes, it is mapped to domain somewhere.
Okay.
Correct.
So
then it is onto. And if there is a unique imaging, then it is 1-1 as well.
But how do I actually differentiate with this information whether it is 1-1 or onto? Because I don't know if 1-1 means there is only one on the domain which is mapped to the codomain, correct?
Yes.
So let me tell him. See, I want to tell you that please be clear with the definition 1-1 and onto. And if you want to be clear, you can do more practice for 1-1 onto for the simple function. Then you can check for this one also. The better way I will say means be clear with the definition of onto, and then you can check for here for this one. So what I mean to say, if in the pictorial form, I will say, so onto says, suppose it is like this. So onto says no image will remain. No image will remain. If I am erasing it here.
Unmapped.
No image will no image will remain to map with a single. Oh, sorry, I made a mistake, I think. Because
it is correct.
No.
For onto.
Different. No, this is not for onto. It is
for bijective.
Okay, this is for
This
bijective.
image is makes sense for onto, sir, because here this is not onto because there's something in codomain which doesn't have a domain. So now it's 1:1. Yeah. And now it's not 1:1, but still onto,
But
isn't it?
yeah, it is onto.
Yeah.
It is only onto. Yeah.
It is only onto. So means there is no image left for that. It have a pre-image.
Yeah.
Yes.
Sir, then if supposing the determinant is not 0 and we have infinite solutions, even then won't it satisfy the onto condition?
No, actually, then it will why it will problem. If it is have suppose determinant is non-zero, or sorry, determinant 0 means to say it have infinitely many solution.
Yes, but then the one you've just given where this image has two two pre-images have the same image.
Okay, so actually the condition is okay. If have yeah, actually you are getting a image for that. So yeah, you can say, yeah, actually you can say, if suppose determinant 0 means to say the system is consistent, means to say either unique solution or infinitely many solution. If determinant is equal to 0, then there is a possibility that it have no solution also, no? So that's why determinant not equal to 0 confirms that it has solution.
Okay.
Determinant not equal to 0 confirms
Is
that
a sure assurance that it will
have a
definitely.
solution. Suppose it is
And
equal
it's
to
definitely
0.
onto.
If suppose determinant is 0, then it have infinitely many solution or no solution also, which will contradict our assumption. But determinant not equal to 0 shows that it have solution. That's why you have able to get a pre-image, exact pre-image, unique pre-image.
Okay, here we have every image is having a pre-image. Okay.
For this one, you have a pre-image.
So how is it that we are able to establish it from the?
So for this one, what is happening? Suppose this is R2 also. This is R2 also. So our map is from V to AV. It says that our determinant is non-zero. It says that our determinant is non-zero means it implies. Hope you know that the system of linear equation when determinant are not zero. In such case, you have a unique solution.
Correct.
Correct. So it means that you are able to find y1, y2. Means as here our system of linear equation for this case, because you are non-zero means you are make it invertible, and like that you are getting the value for y1, y2. So for this case, what is happening? Our suppose this is x1, x2. So when we inverted the matrix here, it will shift it to somewhere here. Says that okay, we are able to get a pre-image. Yeah, actually, what I mean to say, please take your time. You will surely get. Yeah, for such kind of confusion, if you take your time, you will get.
Yeah.
Because yeah, actually, for such, because if you are we discuss, you may get more confusion.
Yeah.
Please take your time. You will surely get, because everything is clear.
It is clear. It is clear, sir.
So please take your time. You will get. You may clear.
Sir,
But just be clear with the definition for the 1 and onto, and try to solve some question. You will surely get. Okay. So can we move to our slide? Actually, I want to discuss for the nullity also.
Sir,
yes,
I
sir.
missed the determinant part. Can you repeat it, please?
A determinant says determinant. Why we are confusing with? We have if this part is clear, then this is the simple system of linear equation we are solving.
No, sir, I missed it. It means I have some network issues.
Determinant
So
has got
I will say,
nothing to
please
do
watch
with
again.
1, 1, 2.
Please, you can watch on YouTube,
Okay,
because
sure. Yeah. I do understand.
And we need to discuss the nullity also. I want, because linear transformation we'll spend lots of time on, and I hope most of the things clear to you for the linear transformation.
Absolutely.
So let's discuss this nullity. We have at least 15 minutes. Then we can extend time. We may extend, but try to be strict on that. So nullity, what is nullity? All of you is clear, no? What is the nullity or what is the null space for a matrix?
A number of independent
Yes, sir.
variables.
Number of independent variable for the matrix.
We can do a
Yes.
quick revision.
Okay. So what is let's do quickly then maybe. What I mean to say, what is the nullity and what is the null space for a linear for a matrix. So the concept came in week 4. You have gone through the rank of, it is not right.
Yes, sir. Rank and dimension.
So in previous week you have gone through if you have a matrix A, okay, if you have a matrix and you know that what is the rank of a matrix. Rank of a matrix is this matrix. If you do the elementary row operation, means R1 R2 time these things are do the operation and try to change this matrix in row echelon form is also enough, or reduce row echelon form. Reduce or row echelon is also been enough. You are able to change this matrix in row echelon form, and when we change your matrix in row echelon form, then number of
Non-zero
rows tells that the rank of matrix is that number.
Number of non-zero rows is equal to rank of that matrix.
Equal to the rank of matrix.
Or sir, we can say the number of dependent variables. Right?
Number of dependent variable. So actually what is happening when you change your matrix in row echelon form? So not only row echelon form, if you are talking with the dependent word, so you need to change your matrix in reduced row echelon form.
Reduced row echelon form, right.
So when you change your matrix in reduced row echelon form, so suppose you are getting like this 0 0 0 1. Let's say here is 1, and this is not in reduced row. Let's say this is 1 and this is 0 0 0. So actually this is in reduced row echelon form. So when we are discussing a number of independent and dependent, we just discuss. I made the best way is write the in front of the column your x1 x2 x3, so it will makes very clear what is happening. So this is going to your leading entry for the first row, and this is going to your leading entry for the first row. This is going to your leading entry for the second row. This is not a leading entry for this row because this is ahead there is 1, and actually this is in row echelon form. All of you properly, or all of you are expecting that all of you know the row what is reduced row echelon form and row echelon form. So this is the leading one, and dependence is leading entry. See, this is the leading one in this column. In this column, if you see that, this is the only non-zero entry here. This is the only non-zero entry in this column is this one, this one. So actually in the reduced row echelon form, if these things is happening, then the corresponding variables work as a dependent variable. This is not a leading entry for this column. So for this will work as a independent variable. And rest for these two, it will work as a dependent variable. So so rank is actually the number of dependent variable, and nullity is actually the number of independent variable. So for this matrix,
opposite of rank.
Opposite of rank. So for this matrix, your nullity will be
1.
That's here 1 independent, so 1. And in different word, see, you know the word nullity, but what is the mean of nullity? So I just quickly revise
no element in the set.
Okay, I just quickly revise this one. But what is the mean of null space or nullity? So what is that? If you have a matrix, this one, okay. So write this matrix as a system of linear equation. In this matrix form, if you are writing, means write this matrix as a system of linear equation in the homogeneous form. This is called the system of linear equation, homogeneous system of linear equation. When your system is like this, and if B not equal to 0, this is called non-homogeneous. If B is 0, then this system is called homogeneous. So think about whenever you have a matrix, think that matrix as a homogeneous system of linear equation. And see, now this kind of system of linear equation either has unique solution or infinitely many solution. It will never have no solution. Either it have unique solution or infinitely many
solutions.
So unique solution in such case it will be 0, 0, 0 only. And when the infinitely many solution have, then this will forms the vector space. So definition of null space is actually null space
0, 0, 0.
A matrix, a set such that AX is equal to 0, collection of these things. And actually this set forms a vector, this will forms a vector space. Actually this is a subspace of a matrix, whatever your X is like X, if your X is like this, only 3 entries are coming or 4 entries are coming, whatever the number of coordinates are coming. So your null space will be the, suppose your coordinate is coming 5, suppose x1, x2, x3 and x4 and x5 are, so this is a subspace of the vector space R5. So null space is actually the collection of solution. And if you form a vector space, so this will be if you form a
solution of homogeneous system of linear equations is null space.
Actually null space the collection of, in simple word I will say, maybe I made a more complex. In the simple way is that null space is the collection of all solution. Set
of a homogeneous linear equation.
Null space is a solution space. And actually that's why we used to say this is a null space. And actually this is form of vector space. That's why dimension word is came. Actually this solution space forms a vector space. That's why dimension word came. And whatever the dimension of this vector have, whatever the dimension of this vector space, that is called the nullity of the matrix. That's all. This is the definition for the null space. And how we will find the nullity? For that, let's do an example. Then it will be more clear. Like I have this matrix. Can you, anyone or all of you, not only one, all of you, can you tell me what will be the entry here?
1 plus
1 plus 1 is 2. First element is 2.
Okay.
Second is 1 3. Plus 2, 3.
This is 3. Okay.
4. 1 plus 3, 4.
3, 4, 5. 4, 5,
and 6.
So all of you are getting how we are putting the entry here?
Yes, we are adding
minimum of ij plus maximum of ij.
So according to this, your ij is happening, and our ij is our mean of ij, and adding with the max of ij. So that's why your entry will come here. Now the process to get null space or nullity, so you need to change it like this. You have to make it in reduced row echelon form or row echelon form. So you have
nullity is 0.
Nullity is 0. Okay. What is the
because
determinant?
two rows would be same.
2 rows are no, 2 rows are different. So nullity, if 2 rows are same, then nullity will be surely greater than 0. Okay, we can do that easily. This is here 3, 4, and this is, oh, then it is going to be tougher. Okay, we can make a easier thing.
So 2 times R2 minus R1.
2 times R2 minus R1. 2 times R2 minus
R1. It means 6 minus 2 is 4. That is R3. 8 minus 3 is 5. And 10 minus 4 is 6.
Okay. What is it? Okay, 2, 3, 4.
2 R2 minus R1.
This is 1 here, and this is 1 here. If you subtract these two, this will be 1, 1, 1. Oh,
that is why nullity. I was saying nullity is 0.
No, the nullity will be greater than, no, it will be greater than.
It will be 2.
So what is happening? What I am doing here?
2 rows are
R3 minus R2 and R2 minus R1. These
R2.
Do these two operations. This will be 2, 3, 4, and this what you are doing, R3 minus R2. So this is 1 here, 1 here, 1 here, and R2 minus R1.
1, 1,
1. This will come. Okay. Now see, we are trying to see, the process tells us that first divide with 2 and do the all, but you can skip those things and quickly do what you can do, you can shift to like first do the R3 minus R2. So this is 2, 3, 4, and this is 1, 1, 1, and this rest all are
0, 0, 0.
The next step is
minus R1 minus R2.
You can interchange the R2 with the R1 and make it up, and it will be more easier. So
1, 1, 1.
1, and this is 2, 3, 4. 0, 0, 0. Now what you can do, R2 minus 2 R1.
Minus 2.
This is 1, 1, 1. This is 0, and this is 1 here, and this is 2 here, and 0, 0, 0. Now see, this is in row echelon form, but we needed in reduced row echelon form. It will easily can do that. So now R1 minus R2. So this is 1, 0, minus 1, 0, 1. Oh, no. R2 minus 2 R. R2 minus R1. Okay. And 2 here. 0, 0, 0. Yeah. So this is now in reduced row echelon form. This is in reduced row echelon form. So number of dependent variable, easy to write here. As this is the leading one, this is leading one. So this says that x2 and x3 is dependent, and x3 is going to be
x3 and
independent.
x3 is the independent one.
So nullity, you can directly say nullity is 1.
1 is the nullity. X3 is
but what is the null space? Now I want to ask, what is the null space?
All the solutions.
It is the solution of this.
We
find the seem to be infinite.
X3 is equal to 0. So,
so write this reduced row echelon form. Try to make it a system of linear equation. So this says that
x2 is equal to minus 2 x3.
x1 is equal to 1.
X is equal to 1.
1.
X1 is equal to minus.
Row by what you will get the system of linear equation here it will be
x1 minus x3 is equal to 0.
x3 is equal to 0 and x2 plus 2 x3 is equal to 0. So x2 is equal to minus 2 x3. x1 is equal to x3.
x2 is equal to
minus 2.
So
minus
now
2.
Assuming x3 is equal to you are getting the solution. X3 is equal to t, x1 is equal to t, x2 is equal to 2t, and x3 is equal to
minus 2t.
Minus 2t.
Minus 2t, no sir?
Yeah, minus 2t. So now I want to
sir, can you put a minus before x2 is equal to minus 2 x3? That way when people come back and look at it.
Okay, sorry. Yeah, this is minus 2.
So now we can write null.
Now the null space will be
null space.
If you are writing in a set form, it will be t minus
2t and
t where t belongs to R. So this is the null space. But yeah, what is the basis of this null space? Basis. Now we need basis.
1 minus 2 t is equal to 1.
Minus 2.
Putting t is equal to 1. So it will give a vector 1
minus 2 and
so this is the basis of null space.
Null space, yeah.
So I hope it makes clear to all of you what is nullity and null space.
Yes.
And on this basis, this is somewhat harder than previous question.
Yes,
So
sir.
what will happen here? Which option is going to true? It's if you add two matrices, the nullity of after adding these two matrices give the nullity of separately adding the nullity of the separate matrices after adding. Is that true or minus? Or when we subtract two matrices, the nullity of the after subtraction, whatever we are getting, that will be exactly the nullity subtraction of nullity of separate matrices.
The option A is though not necessary, I think.
Actually, I need to add here none of also. None of.
Yeah, because this is
Fourth
the
option.
because nothing is looking very conclusive.
I just forgot to add here the option will be none of them also. Actually, we can see how, but the question is how we will quickly do this. See, okay, you have maybe some idea, but how we will quickly do this? So you can see, you can assume the matrices with a simple way, like
Yes,
1
sir.
0 0, and assume B as a 0 0 0.
Yeah.
If we do this with the simple, what is happening here? The nullity of A is what? What is nullity of
Nullity
A?
of one.
One. What is nullity of B?
Two.
Because see, all R vectors are independent. This is in reduced to
Independent.
echelon.
Correct.
And all there is no leading one, so all variables are independent. So here is B is as nullity you are getting 1 and 2. Now put here, now let's add AB is equal to, still A you will get. So
Yes,
again the nullity of AB is equal to 1. So now check that here, this is 1, this is 1, and okay, this is 2. So no equation is not satisfied. Back to here, this is 1, this is 1, this is 2, this keeps -1, this keeps 3. Not satisfied. Here A minus B needed. A minus B. Again, you will get A itself. So again, this is 1 here, nullity is 1. Here is 1 and here is 2. So again, equation is not satisfied. So you can quickly neglect. So if such kind of question is there, take a very easy matrices like 0. See, most of the time you want to neglect something. So if you are playing with the number, take around the 0. Always take around the 0 with the integer numbers, like whatever we are doing. Here 0 means we are taking the 0 matrix and around the 0 matrix as here A, B. So if you want to neglect something, take something around 0 and 0 itself, and make whatever the infer you want and put in the equation and eliminate the options.
Sir, I just had a question. In reduced row echelon form, there is a possibility that we could get the zero matrix.
As here we are getting for the zero matrix.
We can get this.
What is the no. So for non-zero matrix, you will never get reduced echelon form as 0. For what will be the zero matrix? What is the, suppose you have a 0 matrix, what is the reduced echelon form of 0 matrix? 0
Okay,
itself.
it would be 0.
Yeah, 0
Okay.
matrix.
Okay, in that situation.
In that situation, so for 0 matrix, the only you can say reduced form is 0. If you have a non-zero matrix, it will never have the reduced echelon
Yeah,
form.
that has confused how that was possible. And so the answer here is none of the above, right?
Answer is the none of the above.
Okay.
I have one interesting question. Maybe I want to discuss that. It may help to understand linear transformation in more better way. Okay, so let's discuss this one, then we will end the session. It is an interesting question. You have seen in the activity also, but I don't know, I just made it this one. So suppose you have a linear transformation and you don't have the expression exactly. Whatever we do, we have the expression with this form. but but you have given like this only. Consider a linear transformation with such property. So I want expression. What will be the expression? Expression means writing to be like this. So what will be the expression here? Will like for this, if you have these images, how we will get this? Anyone have idea how we will get this here? No. Am I audible?
Yes, sir. Yes, sir. You are audible. But
sir, is it twice x minus y?
Twice x and minus
y.
Okay, well, we will check those. If you are saying okay, I will.
Sir, is it the same question as was discussed in the lecture, like changing the basis?
So
and finding the. I am stuck in this topic, sir.
Actually, what is in the video now? Maybe it will when we solve this. Maybe then if you watch lecture again, then it will be clear. Actually,
Yes,
what
yes.
is happening here? If you see that this vector and this vectors are actually basis, means basis of R2. No. So what in the video lecture says? Actually, basis defines the linear transformation. In the video lecture, this fifth one, this one.
Yes, sir. Yes.
In that, what is happening?
Linear transformation.
Determining linear transformation.
Almost
when
the
you
last
have
one. Almost in the last.
When you have images of something, when you have images of basis element, as here. Here in the video lecture. Okay, let me make. So okay. So the question is how we will deal with this question. If you do the video lecture, sir have clearly explained the process how we can do. Let's discuss also how we can do here. So if you say that 1 1 and 1 minus 1, these two are the element of R2, and actually these two forms a basis. How we can check this is a basis? Easily we can check if you checking the, you know that determinant should non-zero. So easily you can do this is 1 1, this is 1 minus 1, and this is determinant is minus 1 and minus 1 not equal to 0. So that means this is a basis. This is a basis, not a unique. Means this is a basis element. Now, if you have this is a basis element, so suppose you have a general element from R2, xy. This is an element. So this is a basis element. So we can generate this element using these two element, right? Basis using this element basis. Sorry, yes. Element of basis. This is the use. This is the use of basis. No, why we want basis of a vector space? Because we can generate any vector from that vector space using these vectors.
Yes, sir.
That is the importance of basis. Otherwise, why we are trying to get the basis of a vector space? Because if you have an element, we can generate that element using these two. Let's see how it's happening. That's the word. Now you will say what is the use of linear combination? What is the use of the span? So basis actually says x y equal to 1 1 plus beta time 1 minus 1. Why I am writing this one?
Because every point in this vector space is a linear combination of bases. That is one
element. If you see the definition of basis, or maybe span, basis and span also. So span means span of this set is whole R2. On what do you mean by span? Span means the collection of linear combination. Span is collection of linear combination. So I assumed this is an element of R2. So that means there exists a linear combination using these vectors. That's why I wrote linear combination means alpha time this vector, beta time this vector. This is the mean of linear combination. Till here clear what I am saying?
Yes,
To all
sir.
of you, is it clear?
Yes, sir.
Yes, sir.
Yes.
And this linear combination is going to be then our linear transformation.
So let's see that. Now what will happen? So actually we want to find this is we are assumed what I said, this is a basic element. So why I write this equation, because I want to find alpha beta in terms of x and y.
Yes.
Okay, so let's solve this equation. Now this is an equation, and actually this will form a system of linear equation. That's why we studied system of linear equation. So this is alpha plus beta and alpha minus beta. Now if you compare x is equal to alpha plus beta, if you are right like this, alpha plus beta is equal to x and alpha minus beta is equal to y. Now if you want to solve with the Gauss elimination, you can solve. Otherwise we can directly solve here. If you add these two, it will be 2 alpha is equal to xy implies alpha is equal to x plus y by 2. Now if you got alpha is equal to x plus y by 2, so beta is equal to x minus alpha. This is x minus x plus y by 2. This implies 2x minus x minus y by 2. This says x minus y by 2. Means beta is equal to x minus y by 2. So what it means that xy is equal to x plus y by 2 1 1 plus x minus y by 2 1 minus 1. This is the mean, as because just we substituted here just alpha and beta. So what it mean, what it says, what it mean, that means if you take 3 2 an element of R2, an element of R2. So if you want to 3 2 want to write like this in the basis form, so it will be 5 by 2 1 1 plus 1
by 2
1 minus 1. That's why we uses this basis. This is the mean of, means any vector we give any value to xy, any vector of R2 can be generated using these two vectors. This is the use of basis. Now I hope you are getting why we are studied basis, why we did this.
Sir.
Yes, sir.
Yes, sir. Very much. Yes, sir.
Now actually we want a linear expression. So see that. So actually why I made like this, let's see that why I'm doing here. Apply here t, here t, here t. Now see the use of property of that, why we are studying linear transformation. See, if you have this form, you can make it separate, alpha 1 1 1 plus t time beta 1 minus 1. This is the one property of t of x plus y. Now the second property we'll use here. Now alpha is a real scalar number, real number. So alpha will out. This have t11 plus beta t of, sorry, this will be beta t of 1 minus 1. Here is equal to. These are the equal to thing. These are equal to. After this we are moving ahead. Now see what is the use of basis? You see that you reached here, you reached here. Now compare. You have image this one. T of 1 1 you have this. T of minus 1 you have already. So let's do here we did for alpha beta. Let's do here with the more space. So now when you apply here t both side, so alpha as we make it out means this is a scalar, right? This is an scalar. X is real number, y is real number. So as here alpha, this is alpha, so alpha is out. This is 1 1 plus x minus y. This is beta over, and beta is out. This is 1 minus 1. Because t of c v is equal to c t of v. Now we are using second property. Just now we used it first property. Here also we use it. This is the second property. Now x plus y by 2, t of 1 1 is what is that 1 1? 2 1 and 1 3. So this is T of 1 1 is 2 1 plus x minus y by 2. This image is given 1 3. So now apply here. So what will be here? X plus y, and this is x plus y by 2. This is 1 plus here x minus y by 2, 3x minus 3y by 2. This is another one. Now just add these two. You will get x plus, let's make it.
Sir, can you pause
2x plus 2y is.
Yeah, it will be more better too.
Sir, hello. I got till this step. Transformation xy is equal to x plus y by 2 t11 plus okay. X minus 4. After that, I am not able to understand, sir.
Where? Here.
The step above, sir.
Okay.
X plus y by 2 into 2 1. How have you reached this point, sir?
Here, this one.
We have started discussing the question now.
I think at P of 1 1 we substitute the value of P of 1 1.
Just
in the question it was 2 1.
Yes, sir. This one, sir.
Here, this one.
X plus y by 2 into 2 comma 1 plus x minus 4 by 2 into 1 comma.
Where that 2 comma 1 came. So that is from the question. T 1 comma 1 is 2 comma 1.
Okay, here. So actually T of 1 1 is 2 comma 1. We have given this one. Now we are using this property. We have given this one and this one. This one. T of 1 1 is 2 1. T of 1 minus 1 is.
Okay, sir. Now I got it.
So now if you add this, now add coordinate wise, we need to add. Let's add these two. It will be x 3x plus y by 2, and it will be 4x minus 2y
by 2. 2x minus y by 2x minus y.
xy. So see, we got the linear transformation expression we got. So see how many concepts we used, basis we used, span we used, linear property, that mapping property, that x plus y is equal to t of x plus. These two property we used, vector space and basis, this whatever the information we have we used, and then we got the expression. See, whatever you system of linear equation we used.
Yes.
So whatever you have previously studied, everything is used here to find the expression. The system of linear equation, vector, basis, span, dimension. Dimension is the same. Dimension is the same. In the basis, it will come in the word. Linear combination.
Sir, today's lecture was really fruitful.
Clear, sir. Thank you so much.
You explained so well.
Yeah, it's very clear now. I got very confused.
The linkage is very clear now. How one thing is related to another.
So the the next question is nothing, just nothing. I just wrote what I wrote. You have this information and just find the expression and decide. After finding this expression, you know idea that how to check injective, surjective, whatever. We spend lots of time on injectivity, surjectivity means 1 1 on 2. Injective means 1 1. Surjective means on 2. So the sixth question is nothing. Just whatever the process we did, just find the expression, then decide the injectivity, surjectivity. The last one question.
Okay,
so that's all for today. I hope all of you hear what.
Sir, one basic question I want to ask. There was a question in quiz that we have to decide check whether this is a vector space or not. It was a quiz question. Suppose we are able to generate the spanning set or the basis for a vector space, then it is a vector space. Is it true, sir?
Sorry. Can you repeat again?
Sir, there was a question in quiz that we have to check whether the given spaces are vector spaces or not.
Okay.
some 4 options or 5 options were there in that question. I'm asking, sir, if we are able to generate a basis for the vector space, then it is a vector space. We don't have to check all the axioms.
No. The basis word came after the vector space. Means whenever you have a vector space, you have to check those 8 criteria, and in 8 criteria, first check the closure property of, means first 2 property.
It's the closure property of addition and closure property of multiplication.
Closure property of scalar multiplication. Means to say
Sir,
you have to check vector space,
Yeah.
then find the basis, because basis word came after the vector space. Means to say, if you want to find a basis says whenever you have a vector space, you have a basis.
Sir, is the vice versa true or not?
No. There is no. Then if there is no base, there is no vector space. There is no word basis. Basis is for the vector space only.
Okay, sir.
Okay. Whenever you have vector space, then you talk about the basis, dimension, all over whatever the things we will talk about after making a set as a vector space.
I guess answer to the
vector space through basis. We can span vector spaces through basis.
You can span the vector space through basis, just now as we discussed.
I guess the answer to that question was that requirement was to do addition, closed on addition, and
multiplication.
Scalar multiplication. These 2 answers.
Correct. Yeah.
So whatever really
I'll leave it.
And
Sir,
confusion was on additive inverse.
Yeah. Sir, I have a question regarding nullity. Can I ask?
Okay, so okay. Just now I am thinking to end the session. Okay.
Sir, just last one line confusion is that.
So,
sir, if the null space comprises only of 0 vector, is the nullity will be 1 or 0?
So actually, this is a good question. If null space comprises only 0 vector, so nullity is 0.
Nullity is 0.
So actually, why this is? If you have a 0 vector space means only contains 0
element. Correct.
So it have dimension 0. Using that, you can say. So if a null space is only 0, contains 0 only, so nullity is 0.
Nullity will be 0. Okay. Yeah, it was quite confusing because I was a little bit confused between dimension.
Yeah, actually, I want to tell this on. I should to tell in the starting itself also.
Yeah. So I was little confused.
But sir, in the above question, you explained the nullity A plus B is equal to nullity A plus nullity B. In this question,
that is not a null space. That is a matrix.
Matrix,
matrix.
Yeah, both are different. Yeah.
Okay.
This is a single matrix. This is not a null space. Null space is after. What is the null space of this matrix? Now the question is, what is the null space of this 0 matrix? What is the null space of this 0 matrix? Can you tell me?
0.
No.
2, sir.
2.
R2, whole R2.
Yeah. Okay, sir. Yeah. Space.
Whole R2. Because you have 2 independent variable, no?
Yeah.
Yes,
so
sir.
means 2 independent variable mean dimension. Nullity is 2.
Nullity is 2.
Means dimension. Nullity says dimension.
Yeah.
Dimension comes then saying to be R2 because we are dealing with the matrix in real line. So you can say this is the null space of 0 matrix is R2.
R2.
Is it clear?
So, 0 matrix, sir, how dimension is 0, sir? 0, 0, 0, I think dimension is
Actually, this is, you can say for the 0 null space or 0 vector space, dimension is 0. You can take as a convention, you can say. That's I'm not going to prove. This is you can say convention.
Yes, sir, because what I understood about dimension is that dimension is of null space is cardinality of the basis, right?
Cardinal is dimension. Nullity is the cardinality of
basis, right?
Basis of null space.
Yeah. So I am not able to get whether it is 1 or 0. I am still confused.
Okay.
Yeah.
So okay.
Sir, but it's fine. If you will get some time next time, if you can explain that.
Yeah, sure.
Yeah, sure.
Yes, sir.
Sure, sir. And this was very helpful session. We have enjoyed a lot. Thank you
Yeah.
so much.
Thank you so much for joining. Good night
Thank
to
you,
all of
sir.
you.
Yes, sir. Good night.
Good night, sir. Good night, sir. Have a
Good
nice
night,
night.
sir. Good night.
So,
Thank you
sir,
so much.
tomorrow will be a class or
So
not?
next, probably in 9th on. We are probably fixing on 9th.
Yeah.
Oh,
On
Subhajit
9th.
will take that probably.
Okay. Okay.
Thank you so
sir.
much. Good night to all of you.
Good night. Sir.
Good night.